Here we go with Unit 1 review for AP Chemistry on lab skills, measurement practices, and naming. So the first thing we're going to talk about is calculating gram formula mass. This is the mass of 1 mole of any substance. It's found by adding up the atomic masses of all the elements in the compound. You need to pay attention to how many of each atom there are in the formula by using the subscripts. The units are in grams per mole. So on the AP reference table, they give you the GFMs for each element to the hundredths place, so that's what we're going to use for this year. So I've given you two examples here, sodium chloride and aluminum sulfate. You'll notice for sodium chloride there's only one of each thing, so you just add them together and you give the units in grams per mole. For aluminum sulfate, though, there are 2 aluminums, 3 sulfurs, and a total of 12 oxygens, so make sure you multiply the subscripts when you have the parentheses like that. Molarity. So molarity is the most commonly used measure of concentration for solutions. We're going to use it a lot this year. The formula for molarity is moles of solute per liters of solution, which is why we just reviewed how to do moles, because we have to be able to change our measured masses from the lab into moles in order to calculate the molarity. We also need to go backwards from that. If you're given a molarity that you need to create, you have to figure out how much mass you need to add into your solution. So down at the bottom here, you'll see I want to make 350 milliliters of a 0.50 molar solution of potassium chloride. What steps do I need to take to make this solution, and what values will I need? So take a minute and think about that. What sorts of things might I need to find out? Hopefully you have some ideas. So we'll go on to the answer here. So the steps to make this solution. The first thing you'll need to do is calculate the amount of solid needed. Then you're going to add that amount of solid into a container and then add the amount of water that you'll need to make the total volume with a graduated cylinder, or you can use a volumetric flask. For most cases in our class, we'll be using the graduated cylinder, but if you need something to be really exact, then you're going to want to use the volumetric flask. To make 350 milliliters of the 0.50 molar potassium chloride solution, the first thing you're going to need to do is figure out how many moles of solid you'll need. So you're going to set up your formula. You have 0.50 molar equals X moles over 0.350 liters. You'll notice I had to change my milliliters into liters by dividing by 1,000. Don't forget to do that. That equals 0.175 moles of potassium chloride. Now that's great, but we can't measure moles using our scales, so we're going to have to change the moles into grams. To do that, you need to find the GFM of potassium chloride, which is calculated there, and then you do your math for that conversion. So 0.175 moles of potassium chloride multiplied by 74.55 grams of KCl over 1 mole of KCl, and that is the calculated answer you get from your calculator. However, are we supposed to have that many significant figures? No, of course not. So you should only have 2 sig figs based on my molarity measurement, which was 0.50, just 2 sig figs, so I'm going to measure out 13 grams of potassium chloride. The next we're going to talk about is dilutions. Performing dilutions is another common thing we'll be doing this year. To do a dilution, you're going to be given, or you're going to make a concentrated solution, which is also called a stock solution, and then you're going to need to dilute it down to the lower concentration that you actually want to use. The formula for dilution is M1V1 equals M2V2, where M stands for molarity and V stands for volume. For here, it doesn't really matter what your volume is in as long as you're consistent. So if you're using milliliters, you need to calculate milliliters. If you're using liters, you need to calculate liters. After you've solved your formula, you'll still need to figure out how much water to add to actually dilute that. So we're going to go through an example of dilutions as well. So using the 350 milliliters of our 0.50 molar potassium chloride solution, we're going to make 250 milliliters of a 0.080 molar solution. We do not want to use all of our stock solution, so we're going to use our formula to figure out how much of that concentrated 0.50 molar solution we're going to need to dilute it to 0.080 molar. So when we set up our formula, our X is going to be what volume of the stock solution, or the 0.50 molar solution. When you solve that, your X is equal to 40 milliliters. You'll notice my volume is consistently milliliters there. You're then going to take that 40 milliliters of the stock solution out and put it into a new container. Now, to get it to 0.080 molar, we're going to have to dilute it with some amount of water. How much water are we going to need to add? We want a total of 250 milliliters, and we already have 40 of our stock solution, so you should subtract the 40 from the 250 to get 210. And you're going to add the 210 milliliters of your water to the 40 milliliters of your stock solution, and your final solution should have the concentration that you want. Our next major topic is going to be significant figures. I know, everybody loves significant figures. They are very important to the AP Chemistry exam. At the conference I went to this summer, the man in charge told us that they're not super concerned with you having the exact correct number of significant figures. They give you a leeway of 1 or 2, but you need to have, you can't just write down everything. So it's important that you have some idea how many significant figures you're supposed to be using. I will be looking for significant figures throughout all the labs this year, so you'll be losing half points throughout the year if you don't pay attention to them. So here I give you the example of the one we just did where my molarity only had 2 significant figures, so my mass should also only have 2 significant figures. Also, your lab equipment that you're going to be using throughout the year can only be read to a certain place. So you need to be careful when you're reading your lab equipment, and then you also need to make sure that you keep that in mind when you're doing calculations with the measurements that you just did. When you are reading lab equipment, you always estimate the last decimal place so that you're being as accurate as possible. For looking at just a number that you're given and figuring out how many significant figures there are rules. These rules are written out for you on page 14 of your text if you want more detail, but here's just the summary of them. So non-zero integers are always significant, so any number 1 through 9. For zeros, any leading zeros are not significant, so that number there, the 0.0025, only has 2 sig figs. Those 3 zeros at the front are just placeholders and have no meaning. Zeros between integers are significant, so any 0 in between 2 numbers would always count. And zeros at the end of the number depend on whether there is a decimal point or not. So 100 only has 1 sig fig, while 10, 10 with a decimal point, has 2 sig figs. So the 1.000 times 10 to the fourth has 4 significant figures. That's a way to get a number that ends in zeros to have a certain number of significant figures. Like if you wanted 100 to have 2 sig figs, you couldn't write it as 100, 100, or 100 with a decimal point at the end. You'd have to change it into scientific notation first. The last rule here is exact numbers. These are numbers that can be assumed to have an infinite number of significant figures and will not limit the number of sig figs when they're used in a calculation. For example, if there are 5 pennies, there are exactly 5 pennies. It's not like you have 5.1 pennies or 5.0002 pennies. You have 5 pennies. So some constants can be assumed to be exact numbers, and they don't play a role in determining the number of sig figs when you're done with your calculations. The next thing we have is reading lab equipment. For lab equipment you are actively measuring, you will read to 1 decimal place past what is marked on the equipment. So if it's marked every 10, you should read to the ones. If it's marked every 1, you read to the tenths. So there's 4 pictures here for you to try looking at and see if you can figure out what the significant figures are for each thing. Okay, hopefully you had some fun with that. So the first picture, you're going to read that to the tenths place. The second picture you read to the hundredths place. The third picture you read to the ones place. And the fourth picture you would again read to the hundredths place. Please bear in mind on that last picture you'll notice the numbers are going down, so make sure you're paying attention to which direction the numbers are moving in as well. All right, math with significant figures. So you're also going to have to do some calculations with the numbers you measure or that you're given, and you'll need to round your calculated answer to the correct number of significant figures. I would recommend not rounding until the very end of your calculation so that you're not losing information as you go. There are 2 sets of rules for math with sig figs. The first are for addition and subtraction. We don't do a whole lot of addition and subtraction, but just in case it comes up, the final answer should have the same number of decimal places as the least precise measurement. So for example, if I have 5.68 plus 7.5 equals 13.18 on your calculator, You can only go as far as the tenths place. You're going to round that to 13.2 because 7.5 only goes to the tenths place, while 5.68 goes to the hundredths place. You want to use the least precise measurement. For multiplication and division, which we use a lot more often, the final answer should have the same total number of significant figures as the measurement with the least total number of significant figures. So here, in our example, we have 14.2 times 3.5. 14.2 has 3 sig figs, while 3.5 only has 2, so our final answer should also only have 2. So when you write this out, our calculated answer was 49.7. So we need 50 to have 2 sig figs. So you'll notice that I put the decimal point there to make it have 2 sig figs. Naming review. So hopefully you guys all remember how to name chemical formulas. So we're going to do just a quick naming review here. There's two different circumstances for naming. Either you're going to be given the formula or you'll be given the name and then asked for the other. So if you are given the formula, you need to follow these steps to get the appropriate name. The first thing you want to do is check to see if the first thing listed in your formula is a metal or a nonmetal. If it's a metal, does it have more than one positive charge? If it does, then you're going to need a Roman numeral in the name to indicate which charge it is using. If it is a nonmetal, then you can use the prefix naming system. The second thing you want to do is make sure you change the ending of the second element to "ide." However, if the formula contains any polyatomic ions, you need to use the name of that ion. Do not change it in any way. Just as a reminder, on your AP reference tables, it does not show you the charges that are available for all of your metals. So you might want to use your Regents reference tables to help you remember which elements have more than one positive charge for the moment. You will need to memorize this information so that you'll know which times you need Roman numerals for in the future. Here we have 3 examples to practice on. The first one is Na2O. If you look those things up, you'll see that sodium is a metal. It does not have more than one positive charge, so you can just name it as it is. That would be sodium oxide. The second one, FeNO3,3. Fe is a metal as well, but it does have more than one charge. You need to figure out what that charge is. To do that, you look at the second half of the compound, the NO3. If you find that NO3 has a -1 charge, there are 3 of them, so your Fe must be taking its +3 charge. So this one would be iron 3 nitrate. And then the last one, N2O4, both N and O are nonmetals, so you can use the prefix method here. The prefix method, you literally write how many of each atom there are using the prefixes. So this one, there are 2 nitrogens, so that would be dinitrogen, and there are 4 oxygens, which should be tetraoxide. For the other case, if you're given the name, the steps are to look up the symbols for the elements or polyatomic ions, then determine the charges of the elements or polyatomic ions. Then you want to crisscross the charges to determine the ratio to create a neutral compound. If the name contains prefixes, you just use the numbers provided as the subscripts, and if the name contains a Roman numeral, that is the charge on the first element listed, so you don't actually have to look that one up. And again, we have a couple examples here. First one is aluminum chloride. The symbol for aluminum is Al, and chloride is Cl. The charge of aluminum is +3, and chlorine is -1. So if you crisscross those, you should have 1 aluminum and 3 chlorines. The second one we have is lead-4 oxide. You'll notice the Roman numeral there is referring to the charge on the lead. So lead has a +4 charge in this compound. The symbol for lead is Pb, and the symbol for oxygen is O. Lead again +4, oxygen -2. Now the trick here is if you have multiples of something, you do need to reduce it down. I don't need to have 2 leads and 4 oxygens. I need only 2 oxygens to balance out that +4 from the lead. So you do need to kind of think it through a little bit. The correct formula here should be PbO2. The third example, calcium sulfate. Calcium has a +2 charge, and sulfate is a polyatomic ion with a -2 charge. Since the charges are equal, you don't need more than one of each of them, so the formula should be CaSO4. And then the last one, diphosphorus pentoxide, gives you the number of each atom using the prefixes, so you literally should just write them down. So there are 2 phosphoruses from the di, and there are 5 oxygens from the pent, so it should be P2O5. All right, here's your book assignment. This should be done in your class notes or somewhere where you can have them available for reviewing for the test. The questions that are listed are at the end of each chapter, which refers to the textbook that you'll be using. And that's it. Okay, welcome to AP Chem.